Okay, so welcome to week 7, and before we can start the lecture, I'm going to talk about the field trip to Blue Scope in Wollongong. Just give me one second. This one is too high. So you know that we are going to have a visit to Wollongong next Tuesday. If you want to attend, you have to register yourself to the field trip group. You can find that in the groups folder. And if you would like to have more information about the field trip, you go to the field trip folder where you're going to have the instruction about the visit, the fundamental serial production, and the destination to Wollongong if you want to go by yourself. But actually, we have a bus which we hired. This can carry 22 students, and so far we have 12 students has been registered, and we can still have the capacity of another extra 10 students to be join the trip, field trip. Okay, if you want to check who's there, I'm not sure if you can see that, but actually this is the names of the students who already been registered for the trip. I'm going to talk about this one later when more students to show up. So we will start now with the lecture contents, and for week 7, we're going to cover the next topics. First, we're going to talk about the grinding and other appraisal processing, which type of the machining, traditional machining processes depend on the removal of the material by having a tool. So first we're going to talk about the grinding and the related appraisal processing, which can do the same process of the grinding process. Also, we're going to cover something called the non-traditional machining, which are the new age technology for the machining process. And all these approaches we're going to talk about, like the mechanical energy, the electrochemical, the thermal energy, the chemical machining, and the other application consideration, all these 4 types actually is going to do the cutting with no direct contact between the cutting tool, because we don't have cutting tool, and the part itself. You may know some of this technology and you may use some of them, but we are going to have more details about the 4 different categories for the non-traditional machining. So first we start with the abrasive machining. Now you remember in the traditional machining, what did we use to remove the material? You remember the drilling, the milling, and the turning. What did we use to remove the material from the part to make the shaping? Yeah, which is cutting tool. So we use cutting tool. The drilling cutting tool have 2 edges minimum. We said that the milling have multiple cutting edges, and the turning have minimum of 1 cutting edge. Just remove the material as a chip format. Now, usually we have another process to do the removing of the materials, which by using an abrasive surface. I will show you an example for that before we're going to go through this one. I think you saw this process before. It's called the grinding process. Just remove a smooth layer of the material as a powder format. It's not going to be chip. The chip is going to be in powder format to get a new surface. That's the most common example, you know, the sandpapering, right? To make a new surface. Just remove it by using a grinding material, which is going to be the sandpaper itself. The difference between this process and that process is that we're going to have the wheel, which is going to be abrasive. In this case, we put the material on the paper to get the same effect. So you can see that the difference is that the chip we are going to have generated from the cutting operation is going to be in a powder format, too fine. It's unlike the one we had in the cutting operations. So the definition is a material removal by the action of a hard abrasive particles, usually in the form of the bonded wheel. It's generally used for the finishing operation, not cutting operation, but still it's used for the cutting operation, but not for the shaping. The grinding is the most important abrasive processes, and the other abrasive processing can be the honing, the lapping, the super finishing, the polishing, and the puffing. The advantage are Can be used on all types of the materials. Doesn't matter, it's going to be metal, non-metal, ceramic, plastic, all we can do the grinding for. Some can produce extremely fine surface finishing, up to 0.025 micrometers. And now I think you know what the meaning of that when you did the surface roughness test. Some can hold the dimensions to extremely close tolerances. Have you seen the example for the grinding? Yes, it's everywhere. Even your glasses actually has been done by the grinding process, which is known as the lapping. And we're going to talk about this one soon. So as we mentioned once again, we can have it as a wheel shape, or we can, that's how the idea started. So this is the grinding process to have a good surface finishing on the shaft. Grinding is a material removal process in which the abrasive particles are contained in the bonding grinding wheel that operates at very high surface speed. And the grinding wheel usually is going to have a disc shaped, and this pressure is going to be balanced for high rotational speed. Something like the car wheel. You don't want to have vibration on that. The grinding wheel consists of the abrasive particles and bonding materials to hold these particles in the shape of the wheel. The particles will accomplish the cutting, and the bonding material is going to hold the particles in place to establish the shape and structure of the wheel. The grinding wheel parameters are the abrasive material itself, the grain size, because we have the big particles and small particles. We call them the fine or the coarse. The bonding material properties, the wheel grades, and the wheel structure. The properties of the material first, we have the high hardness. It should have wear resistance because it's going to do the cut. So it should have high resistance for the wear. And it should carry some toughness and the ferrability, which capacity to fracture when the cutting edge is going to be dull. So we're going to have a new sharp edge is going to be exposed. If we're going to have the wheel, which doesn't have the ferrability, at a certain stage we are going to have very fine surface and not going to do the cut. So it should have a good ferrability properties which can break up, generate always a rough surface, which can do the grinding process. So depending on the abrasive material we can have, we can cut it on different types of the materials. The hardness of the different materials like the aluminum oxide, the Al2O3, the knob hardness is going to be up to 2100. The diamonds is going to have the highest types of the hardness of 7000. Okay, now usually we stuck with these two parts because of the cost. Unless if you'd like to have to do the grinding for a very high material, I will go for the other two types. Now just remember that the diamonds will not be able to cut the steel. You remember that from last week? While the cubic boron nitride, which is next in hardness to the diamonds, can do the work on the steel. I think you saw these shapes before. Now you can see it's starting from fine to coarse. That's depend on the grain size and the process we make in these grains about. So the smaller grain size produced for the better finishing, while the harder one, the larger grid, is going to make more removal of the material. That's obvious. Something like, once again, when you do the sandpaper, if you are going to use the fine grade, you'll have a good surface finishing. If you are going to use the coarse one, you're going to remove the material at higher rate. Okay, so removal rate with the larger grids, the smaller grids for better finishing. The hard work materials require a smaller grain size to cut efficiently. For the softer material requires a larger grid size to remove the material at higher rate. Now to explain the grain size, if you know about the meshes we have. Now you can see that number here is going to increase. This one, that means it's going to generate small particles. It's going to only let the small particles to pass through it. The mesh with less number is going to allow for the bigger particles to pass through. Now these numbers, the 10 and the 60s and the 16, 20, 30, that means how many grids we're going to have in 1 square centimeters. So more number, that means is going to be smaller opening for the particles to pass through. We're going to talk about this one the week after this UVAC when we're going to talk about the powder metrology. So the grid size is measured using the screen mesh procedure. Smaller grid size indicated a larger number of the screen and vice versa. So the bigger is going to have a bigger size of the grid. The grain size in the grinding wheels typically in the range between 8, which is very coarse, and 250, which is going to be too fine. The bonding materials properties are, first is what must withstand the centrifugal forces and the high temperatures during the grinding process. Should hold the particles, the grids, while going to have a high temperature due to diffraction and the high vibration and the high velocity of the turning. Must resist the shattering during the shock loading on the wheel. If you are going to hit the part suddenly with the wheel, it should resist the fracture because this is going to be very dangerous during the operation of the grinding. Must hold the abrasive grains rigidly in place for cutting, yet allow the worn grains to be dislodged to expose the new sharp grains. So it's hold to a certain stage, but it should allow it to go to get a new rough surface for the maintaining of the wheel surface. In general, the wheel structure refer to the relative spacing of the abrasive grains in the wheel. So we have particles and bonding materials. You are going to shape them in the wheel shape. Definitely, we are going to have some spaces between the particles. You cannot compact them to the closed shape. Whatever the space is going to be, but there will be space anyway. So if I'm going to add the volumetric proportion of the grains, the bond materials, and the pores, which are the cavity between the particles, we're going to have the volume of 100%. So this is the geometry. We have the bond materials. These are the bond materials connecting the particles, and in between them we are going to have some pores or the air gaps. That's 100% volume, which is going to be the addition of all the volumes we had in this 1 cubic volume. So it's referred to relative spacing of the abrasive of the grains in the wheel, measured in the scale from open to dense. The open structure means that the value of the porosity is going to be large, and the BG, which is the grain value, is going to be relatively small when the clearance of the chips must be provided. Dense structure means that the PB, the particles, is going to be relatively small, and the PG is going to be larger, and we're going to have better surface finishing and dimensional control for the workpiece. The wheel grade, we mentioned that we can have soft or hard. It simply indicates the bone strength in retaining the abrasive grain during the cutting, and that depends on the amount of the bonding materials in the wheel structure. What the percentage of the PB in the volume of the structure wheel. It's measured from scale soft to hard. The soft wheel are going to lose the grain radially, used for the low material removal rates and hard work material. The hard wheels retain grains, used for the high stock removal rate and soft work material. So depending on this scale, from low to high or from soft to hard, depending on the workpiece, the low is going to do the hard and the fragile materials. The high type is going to do the soft and the tough materials. For the contacting area, usually the low is going to have wider contact. The high type is going to have a narrow contact. The rotation speed of the grinding wheel is going to be high in the case of the low type and lower in the case of the hard types. And the rotation speed of the workpiece itself is going to be low in the case of the low type and high in the case of the hard type. The different grinding wheels shapes we can have. This is a cross section for the things. Okay, you can have it either at the straight type, the resist two sides, and we can have it as what we call the metal wheel frame with the abrasive bonding materials on the surface. So actually, this is a cross section for a thing. So it's actually going to be a wheel, and over the wheel we can add the bonding material with the grain, and so we are going to simply we can remake this one by removing the material and coat it once again. Something like when you change the tire after the time life. Also, we can have the abrasive cut-off wheel. This is not going to do the surface finishing. Actually, it's going to be used for the cuts, and that's what they use in the manual grinder. For the surface finishing, which is the most grinding operation are performed to achieve a good surface finishing like what we have here. The wheel will go forward and backward oscillating, and is going to remove the materials by the direct contact with the surface. Best surface finishing is going to be achieved by, if we're going to have this small grain sizes as we mentioned, higher wheel speed and denser wheel structure, because this will remove the material at lower rate and is going to remove it at less rate of the removal of materials, and also because they are going to be dense, we are going to have the best surface finishing. The different types of the grain actions are, we can do the cutting. If I'm going to insert the grain at most depth of cut inside the work material surface. I can do the plowing, which removing the material at lower rate, and I can do the rubbing, which is just going to finishing the unwanted parts, which are going to be appear as in edges, but not the whole surface. So the cutting is cutting grid projects far enough to the surface to form the chip, and thus the material is going to be removed. For the plowing is the grid projects into the work, but not far enough to cut. So the surface is going to be deformed and the energy is going to be consumed. For the rubbing, the grid contact surface only by rubbing the friction occurs, which is going to consume energy, but is going to be no material is going to be removed in this case. Usually, because we are going to have friction, because of the direct contact between the wheel and the part, we are going to have high temperature to occur in the grinding process. This temperature is undesirable because it's going to have a damaging effects on the part itself. The surface will burn and it cracks. We can have some metallurgical damages immediately beneath the surface because the change in the crystalline shape of the materials just below the surface, the whole surface. It's going to cause softening of the work surface if the heat is going to be treated, and residual stress in the work surface because of the higher pressure we're going to have due to the temperature changes of the volume. Now, just remember these points. Okay, that's what the effects of the temperature during the grinding process. Now, to get rid of these effects, we can do the following. First, we can decrease the infeed, the depth of cut. So instead of doing the cutting, we can do the plowing. Reduce the wheel speed. The speed of the friction is going to be less. Reduce the number of the active grids per the square inch of the grinding wheel. So we go a little bit coarser than the deniser. And increase the work speed, the oscillating velocity, and use the grinding fluid, which is going to be something like the cutting fluid, which do the cooling process in the case of the machining process. So usually we're going to have the wheel wear during the operation. Now that's the bonding material holding the diamond grids, for example. When they're going to do the removal of the material, is going to have some fractures. At a certain stage, this should be taken off. Otherwise, we are going to have very fine surface for the wheel, and thus there will be no operation. We're only going to have direct contact, but we're generating the heat, but no removal of the material is going to occur. Why we have the wheel wear? First, because the grain fractures, as we saw in the previous diagram. As the edge going to be fractures, the area becomes new cutting edges, and tendency for the grain fractures is called the variability, as we mentioned, and we need to have this deferrability to be happened. We have some of the arterial wear which drilling of the individual grains, resulting in flat spots and rounded edges. And this is very unwanted process. It's analog to to tool wear in the conventional cutting tool, caused by similar mechanism as the conventional tool wear, including diffraction, diffusion, and the chemical reactions. One of the other causes are the bonding fracture itself. So it's holding the particles start to fracture due mainly to the high temperature. Depending on the wheel grade, among the other factors, usually occurs because the grain are become dull due to the attrition of the wheel, and the resulting of the cutting forces become excessive, so the wheel will simply shatter because of this fracture. So the diagram of the tool life or the wheel life is going to be something similar to what we have in the case of the cutting tool. We're going to have the initial wear, the continuous processing wear, then we're going to have the accelerated wear until we're going to have the final tool life or the wheel life. So we can simply get the wheel wear curve to be the GR, which is the grinding ratio, is equal to the VW, which is the volume of the work material removed, divided by the VG, which is corresponding volume of the grinding wheel worn. After the wear of the wheel, we can simply give it a new life by doing the process which is called the dressing of the wheel. Now, some of the students in the final exam, they are answering this question wrongfully. When we mention the dressing of the wheel, that doesn't mean we are going to add another layer. No, we are going to remove the layer to get a new surface. So the definition of the dressing the wheel is going to be resharpening of the wheel. And this accomplished usually using by that wheel, the rotating disc, or using the abrasive sticks like that, the abrasive sticks, or any other grinding wheel held against the wheel being dressed as it's going to rotate. So the function of the dressing of the wheel is going to be break off of the dull crest to expose the new sharp grains and remove the chips clogged on the wheel. And this is required usually when we're going to be in the third region of the wear curve in this part. So simply we have to give it a new life by doing the dressing of the wheel process. Now we talked about first once again the rotating disc. These are the rotating discs, and we can have it with the cutting tools, and we can run another wheel opposite direction of the grinding wheel, or we can simply use what we call the grinding sticks, which are these sticks. We just expose it to the surface, and it's going to do the cleaning for the surface and generate a new face for the wheel. We have 4 types of the surface grinding. The first one is going to be horizontal spindle, as you can see here, with the reciprocating table, which is going to go forward and backward with the work part. So this one is rotating, and this one is oscillating and moving on the left and right for the wheel. So that's why we're going to cover the whole area. The other type is going to be horizontal wheel spindle with a rotating work table. So usually this will be for the disc-shaped parts. We can have the vertical spindle, and the contact is going to be the face instead of the side of the wheel. And we're going to have the oscillating table going forward and backward. And the last type is going to be the vertical wheel with the rotating table. Other type, surface grinder. This will be the machine for the surface grinder. This is the oscillating table, and this is your horizontal shape of the wheel. So this will be the contact. The part is oscillating forward and backward. The wheel is feeding to inward each time we are going to cover one of the surfaces. Now, usually, the part to be held on the machine by using electrical magnets. Okay? Unless if you're going to use, for example, aluminum, you cannot hold it like that. You need to use your vise. The cylindrical grinding process is going to be required when I'm going to do the process of grinding the shaft, for example. So in this case, both the workpiece and the wheel are going to rotate, and their rotation usually is going to be in the same direction. This can be done externally and internally. So that's how we hold the parts in between the grinding wheel. Usually we're going to have the parts going to be held in an inclination. We have two different types of the grinding, which are the creep feed grinding process. Now, that's the normal case, the conventional surface grinding. We just remove the material at very thin layer to expose a new good surface finishing. But sometimes we can use the same process to remove the material at higher rate to even make the shaping. And that's what we know it as the creep feed grinding, where the depth is going to be 1,000 to 10,000 times greater than the conventional surface grinding process. The feed rates are going to be reduced by almost the same proportion. So because we're removing the material at higher rate, we cannot do it with the same velocity, so we reduce it by the same value. If I'm going to increase the rate of the depth by 1,000 times, I have to reduce the velocity by 1,000 times. The material removal rate and the productivity are going to be increased in the creep feed grinding because the wheel is going to be continually cutting. In conventional surface grinding, the wheel is going to be engaged in the cutting for only the portion of the stalk length. Other processes which are similar to the grinding process because they are using the abrasive surface like that is going to be the honing process. Now the honing process is something like I cannot say it's something like the reaming, but actually it's something like the grinding, but it's going to be for the internal cylindrical shape. So that's my device. It does have multiple contact area which is going to be quite rough, and it's going to be used to do the finishing for the internal combustion engine cylinder surfaces, performed by the set of the abrasive stacks on the cylindrical shape. It's going to have both rotational and the oscillating motion. So this device is going to be rotating and going forward and upward and downward. Of course, it should be combined with the cooling fluid. Common application to finish the bores in the internal combustion engines. The grid size for the stacks is going to be something between 30 and 600. The surface finishing is going to be something about 0.1 micrometers or better. And it creates a characteristic cross-section hatch surfaces that retain the lubrication. So we do that on purpose. Usually we can do it as a mirror shape, but we need to get some cross-hatch surfaces to retain the lubricant during the operation of the engine block. So this is the honing process. Now, other abrasive process usually not going to be used for the metal. It's called the lapping. In the lapping, we're going to use a suspension, a slurry material. So we put on the surface we would like to do the grinding for, and we have the tool which is rotating, and thus we're going to have the particle which do the grinding process. That's the lens. That's how we do the grinding for the lens. Because if we're going to have direct contact between the tool and the work part, we're going to have scratches and even a fracture for the part. So does that remind you of something? Now, actually, polishing of the car is going to be a similar process to the lapping. So once again, we use the fluid suspension of very small abrasive particles between the workpiece and the lap. The lapping compound are going to be a fluid with abrasives. General appearance is going to be chalky paste. The typical grid size is going to be something between 300 to 600. And the application are going to be for the optical lenses, the metallic bearing surfaces, and the gauges. Now, once again, do you remember what 300 to 600 now? Is that going to be coarse or fine? The high number means going to be finer. Okay, because the number of the grids we are going to have in the 1 square millimeters, a centimeter is going to be higher. The super finishing. Now, we always talk about the super finishing. Similar to the honing, use the bonded abrasive stacks, which are going to be passed against the surface with rotating motion. So it's going to go forward and backward. The part is rotating but very slow, and the oscillating speed is going to be very high. And that's why we're going to have something like the mirror shape. And that's what you're going to see in the shaft you're going to start to work on for the major project 2, the gear pump. So that's how it's worked. The difference between the honing and super finishings are shorter stroke, so it doesn't have to go all the way down. Higher frequency is going to be used. Lower pressure between the tool and the surface, and we're usually using the smaller grid size to get a better surface finishing. Now, everything we covered so far was a direct contact between the tool in the drilling, the milling, the turning, the broaching, the other processes, the grinding. But the new technology usually tries to avoid that. Can you give me an example of non-traditional machining processes? No direct contact between the work part and the cutting tool. The laser cutting. We're just using the light to do the cutting procedure. The water jet, using the water to do the process. So, definition of non-traditional processing are: any traditional machining is based on the removal of the materials using the tools that are going to be harder than the material itself. Non-traditional machining process, first, they do not use a sharp cutting tool as in the conventional sense. Non-traditional processes are a group of the processes that remove the excess materials by techniques involving mechanical first, thermal, electrical, or even chemical energy, or simply we can do the combination of mechanical, chemical, mechanical, thermal, electrical, chemical, and so on. All have the common process of no contact between the cutting tool and the work part. So the advantage we're going to have from that are, it can machine the newly developed metals, which are going to be too hard to be done in the conventional cutting. We can simply form an unusual and complex parts geometries that's going to have cannot be readily to be accomplished by the conventional machining. For example, if I would like to drill a hole which is going to have the ratio length to diameter of 100, that means the length is going to be 100 times longer than the diameter. So you cannot do that using any drilling. You can make a hole with 0.5 millimeter diameter, an inclined hole, cleaning the cavity for the water in the engine block, the cooling cavities. You can use it to, for example, cut a very thin material, which cannot be cut by the process of direct contact between the cutting tool and the work part. Also, it's going to reduce the risk of surface damages that often accompanies the conventional machining. So the types of the non-traditional processes: mechanical, which you're going to use the mechanical erosion of the work material to do the cut, like the ultrasonic, the water jet, the abrasive water jet, the abrasive jet machining, the abrasive flow machining. So from the name, in all the cases, we are going to use an abrasive material, but it's not going to be in the wheel format. It's going to be usually in solution format. The electrical types, like the electrochemical machining, the electrochemical deburring, and the electrochemical grinding process. The thermal types, which are going to use the heat to fuse and vaporize the metal, like the electrical discharge machining, the electrical discharge wire cutting, the electron beam machining, laser beam machining, the plasma arc cutting, and the conventional thermal cutting processes. And finally, the chemicals, like using the chemical reaction to do the work, like the chemical millings, the chemical blanking, the chemical engraving, and the photochemical machining process. So this is the first operation. Almost the same slurry we use in the lapping process, but instead of doing the rotation of the tool to do the process of the grinding, I'm going to use a tool which making an oscillation at very high frequency. So no contact between the work part and the tool. The tool is oscillating, and this will cause that the slurry particles will hitting the part and start to remove the material, and we have the cutting to be happen. Because we want to send the material away from the parts and the work part and the tool, I should have the flow continuously for the slurry material to clean up the area. So the ultrasonic machining, or the USM, is a process contained in a slurry are going to be driven at high velocity against the work by simply a tool vibration at low amplitude at high frequency. The tool oscillation is going to be usually perpendicular to the surface. The process accomplishes the material removal. The tool is going to be fed slowly into the work part, and the shape of the tool is going to be formed in the part. If I'm going to have the cutting tool is going to be triangular shape, my hole is going to have triangular shape, cylindrical or elliptical, and so on. So definitely you know that we don't have another machining process to do the triangular cut, for example. This can do it. So that's what will happen in the case of the mechanical ultrasonic machining process. That short video will explain the things. Very simple method. So we're applying the slurry on the surface. It's going to be continuously running. My tool is going to be oscillating. This causes the particles to do the removal of the materials. And by the end of the process, after the slow feedback of the cutting tool, we're going to have the shape of the tool generated on the surface. Well, something like the sandblasting actually, but we're going to have it in the fluid, and we're going to have the vibration to cause the hitting of the surface with the particles. So the application of that first is going to be for the hard brittle works materials such as ceramic, the glass, and the carbides. Also, it's successful on certain metals such as the stainless steel and the titanium. The shape will include mainly the non-round holes and the holes along the curved axis. The coning operation is a pattern tool. Pattern on the tool is going to be implemented on the flat work surface. So like that, we're going to have the pattern of the tool is going to be shaped on the work part. The other process, which is very common nowadays, is the water jet cutting. You may face that before moving near the water tube with a hole and spraying the water. If you put your hand, you will feel the heat. Actually, the same idea gave the scientists back in the late 70s, early 80s on using this pressure force to do the cutting of the metals and non-metals material. So it's going to use high pressure, high velocity stream of the water directly on the work surface for the cutting operation. The application usually is going to be automated. The cutting tool is going to be automated by using the CNC or industrial robots to manipulate the nozzle along the desired path, simply because you cannot hold it with hand with the high pressure. Used to cut the narrow slit in a flat stock such as the plastic, textile, the composites, the floor tile, the carpet, the leather, and the cardboard. But it's not suitable for the brittle materials like the glass. The advantage, no crushing, no burning of the work surface. Minimum material loss because it's going to cut very thin, narrow curve. No environmental pollution. and it's very easy to get automated. For harder materials, the water by itself is not going to be enough. So they're mixing the water with an abrasive material, and thus we are going to call it the abrasive water jet cutting. So we are going to feed the abrasive materials to the water stream, and thus we are going to have higher effect for the water jet. Additional process parameters are going to be the abrasive type, the grit size, and the flow rate. The abrasive usually is going to be aluminum oxide or silicon dioxide and the granite. The grit size is going to be something between 60 to 100 in size, and the grit added to the water stream at about 0.25 kilogram per minute after this stream is going to exit the nozzle, because if you're going to add it before the nozzle, it's going to wear the nozzle itself. The application usually is going to be performed manually by operator who aims the nozzle, normally used as a finishing process rather than the cutting process. The application are going to be deburring, the trimming, and the deflashing, the cleaning, and the polishing. And the work material is going to be the thin flat stock of hard, brittle materials like the glass, silicone, mica, and the ceramic. Another mechanical energy process is going to be what we call the abrasive flow machining. So we're making a paste, and this paste is going to contain the polymers and the grit material. It's going to be tough material. I'm going to pressurize it inside the cavity system, and it's going to do the cleaning process. I will repeat this video again. Okay, so we're making the viscose polymer and force it inside the holes. Where's the mouse? Okay, so that's my work part. I'm going to send the viscose material through the hole. Higher pressure, and thus is continuously running through the cavities and making a good surface finishing from inside. That's something cannot be reached with any other machining processes. So the abrasive particles once again is going to mix with the viscoelastic polymers and force flow through the through and around the part surface and edges, and the polymer is going to have a consistency of the body shape. And the application mainly is going to be for the deburring and polishing of difficult to reach areas of the parts, and particularly well suited for the internal passageways like we saw here in this video that may not be accessible by any conventional method. Now the other method is electrochemical machining.
This way of machining is run without actually having any contact between the tool and the workpiece. The workpiece is charged positively, as you can see, and the tool is charged negatively. And between the two pieces, there's a tiny gap where they don't actually touch, but there's a electrolyte fluid between the two that slowly removes atoms. And as the tool is slowly moved down towards the workpiece, more and more atoms are removed until the workpiece conforms to the same shape as the tool. This is convenient because there is no actual contact, so there's no tool wear and no friction, which causes heat. This can be used for a variety of parts in many complicated shapes, such as a cylinder that has been machined with a sear. And this can also be used for tiny parts.
Okay, now it's electrochemical machining. What do we use the electrochemical for? The plating. Have you ever heard about the plating of the metals? You can put any metal and you put the cathode and the anode. So we have the anode that's going to transfer the electrons of one metal to the surface of the other one. Then we're going to have the things plating. So what's happened actually, one of the parts, which is going to be the positive, is going to lose the electrons to the negative, and thus is losing the material. Now what's happening if I'm going to cut the transportation of the electrons in the middle and push it away? That means that one part is going to lose the material and I'm going to have the cutting. That's what's happening in this process. We're going to have the cathode and the anode. What's happened that if I'm going to stop the streaming of the electrolyte solution, the material is also it's only going to be coating the cutting tool. So to avoid that, I'm going to run the electrolyte fluid, so I'm going to push away the electrons, and thus I'm going to cause the removal of the material from the work part which represent the anode before it's going to be covering the cathode. So electrochemical machining is a material removal by the anodic dissolutions using the electrode in the tool in a close proximity to the work but separated by a rapidly flowing electrolyte. The application usually is going to be for the die sinking, where we can have irregular shapes and the contours for the forging dies, plastic molds, and other tools. We can have multiple hole drilling process, which many of the holes can be drilled at the same time with the ECM. And we can have the holes which are not going to be round. And I can simply have the deburring operation, which removing the edges which generated from the drilling operation or any other machining operation. Now, that's the deburring operation. These are the burr, and we need to remove them. So simply I'm going to use similar machine, but in this case, it's not going to have a cavity. This will be the cathode. It tries to attract the material from this side because it's insulated from these sides. So the transfer is only going to be limited at the between the burr and the cathode. So simply, while the electrons try to cover the cathode, I'm going to send the stream from downward, and this will push away and having the deburring for the edges. I can use the same process to do the grinding process, or what we call it the electrochemical grinding process. The principle are going to be the same. The wheel is going to be the cathode, and the part is going to be the anode, and I'm going to have the electrolyte material. The wheel is rotating, and I'm going to use the flow of the electrolyte material, and thus I'm going to remove the material at very low level to have the best surface finishing on the work part by using the grinding wheel. Now the good thing with this one that the grinding wheel is hardly going to be wear because there's no direct contact between it and the work part. Let's see the video first. So you saw that the wheel actually is not made of a present material and the bonding material because we need it to be an electronic conductor. Okay, so it was metal to attract the ions from the work part, and the solution was able to interrupt this process. The application first is going to be sharpening of the cylinder carbide tools, the grinding of the surgical needles like the one we saw in the video with thin wall tubes and the fragile parts. The advantage are deflating the responsible for 95% of the material removing. Because the machine is going to be mostly electrochemical, the grinding wheel is going to last much longer. The other types are going to be thermal energy processing. Now we are going to involving the heat in the process. Very high local temperatures will cause the evaporation of the metals or the materials and do the cut in this case. Physical and metallurgical damages on the work part or the work surface because we are going to have high temperature in a small area. And in some cases, it's going to resulting in a poor finishing of the parts. The subsequent processes are going to be required in this case. One of the most common applications are the electrical discharge processing. Anyone here like to do the mechanics of the cars? Have you done fixing for your car before? Not yet. Does anyone have old car or motorcycle or mower? You does. Okay. Now, have you ever done by mistake that you try to turn it on while the plug head is off, and you found that the sparks are coming? If this spark going to hit any surface, it's going to itch it. So someone thought about that. Said, okay, now if this discharging, if this electrical spark can do the itching for the surface, why don't simply use it to do the cutting for the surfaces? And he came out with the idea of the electrical discharge processing, where the metal is going to be removed by the series of the discrete electrical discharges or the sparks. Simply, it's going to cause a localized temperature high enough to melt or vaporize the metals. So how to guide it to a location? Simply, we need a fluid to do that. Otherwise, if it's going to be in the air, it's going to go at different positions. So something similar to machine we had for the ultrasonic device, but it's not going to be oscillating. It's only going to feed downward. It's going to have the negative side, and this will be the positive side. It's going to be connected to an electrical circuit. So the spark will be generated, hit the surface, and cause the metal to be removed. We need the electrical fluid to push it away from the location. And thus, we are going to have the cavity to be generated by the electrical discharge. Can only be used if we're going to have electrically conductive work materials. Thus, I cannot use it if I would like to cut the, for example, the ceramic. It's only going to be used if your materials is going to be conductive materials. We have two main processes. The first one is going to be the electrical discharge machining, and we have the wire electrical discharge machining process. The electrical discharge machining operation is one of the most widely used non-traditional processing. Again, to show you something, I'm sure that you saw this one before, but you were wondering how they did it. I will show you today how they did the photo I show you next slide. The shape of the finished work surface is going to be produced by the shape of the electrode tool. The spark goes across the small gap between the tool and the work, and actually this gap is going to be too small. Sometimes you cannot even notice it. It requires a de-electrical fluid, which creates a path for each discharge as the fluids become ionized in the gap. The work materials in the EDM must be electrically conducting, otherwise it's not going to attract the spark. The hardness of this and the strength of the work metals are not factor. Whatever the metal hardness is or softness is not going to be considered because the spark is going to do the work. The material removal rate depends on the melting point of the work materials. Okay? The applications we have mainly is going to be for the tooling of many mechanical processes like the mold we use in the plastic injection molding, the extrusion dies, the wire drumming dies, the forging and heading dies, and the sheet metal stamp dies. The production parts, the delicate parts which are not rigid enough to withstand the conventional cutting forces, or the hole drilling where the whole axis is not going to be acute angle to the surface, sorry, it's going to be at acute angle to the surface, and the machining of the hard and the exotic metals. You see this, saw this one before, right? Have you seen this one before? And you will wonder how they cut it. The electrical discharge wire did that. So the same process, instead of we are going to have the stamp sending the spark, we're going to have the wire doing the process. So we're going to have wire connected between two spools, continuous feeding of the wire to maintain the diameter of the wire, because as the wire is going to send the spark, is going to lose its diameter. and it's going to move and do the cutting of the curve. It's going to be too small, so usually it's going to be very hard to notice it, because this wire diameter is something like the hair diameter. We're talking about 0.25 millimeter diameter. So the wire EDM, now you will ask me how I'm going to withstand the cutting, because actually there's no contact between the work part and the wire. This spark will do the work. The spark will go all the ways, melting the metal, and the wire is going to move to do the shape. So wire EDM is a special form of the EDM that uses a small diameter wires as the electrode to cut the narrow curve in the work. The application is ideal for the stamping of the die components. Since the curve is going to be too narrow, it's often going to be possible to fabricate the punch and the die in a single cut. Other tools and parts within the indirect outlines are going to be outline shapes such as the lathe form tools and the extrusion dies, and the flat templates are going to be possible to be done with the wire EDM. So that's the process. That my wire is going to move around. We should move the water stream once again to send away the cutted metal from the work part. It's actually similar to the bandsaw operations, and usually the CNC is going to be used for the motion control. Usually it's going to be fed very slowly past the wire along the desired path. While the cutting, the wire is going to be continuously advanced between the supply spool and the take-up spool to maintain the constant diameter of the wire. The dedicated dielectrical fluid is required using the nozzle directed on the toolwork interface or simply by the submerging of the parts and the dielectrical fluid. Now, the first process before they start to use the laser to do the cutting, they use the electronic beam to do the machining. Now, to make the electrons transfer between the distance, the condition is that you should have a vacuum. You cannot do that in the air, because otherwise the electron will be disappeared in the air. So you should have the vacuum chamber. You have simply to vacuum the area here. You're going to have the cathode, which is going to be the source of the electrons, and the workpiece is going to be the anode. This anode to direct the things. We're going to have the valve. The electron beam will be generated. We're going to use the magnetic lens to direct the electrons, and we're going to concentrate it in a very small area. Too much energy in a small area will cause the metal to increase the temperature and start to melt. So it's going to use the high velocity stream of the electrons focused on the workpiece surface to remove the material by melting and vaporizing. The applications are going to be the works of any material. Doesn't matter, it's going to be conducting or non-conducting. Ideal for the micro machining process. Can drill small diameter holes with down to 0.05 millimeter diameter, cutting the slots only to about 0.025 millimeter wide, drilling holes with a very high depth to diameter ratio, and the ratio is going to be greater than 100 to 1. That means that the length is going to be 100 times longer than the diameter. So just imagine if you're going to have this diameter and the length is going to be 0.5 millimeter, you say, okay, now that's too small, but actually this cannot be done with any other operation. We have something called the nanotechnology. When you do the micro machining for the small part, where you can see only by the microscope, you cannot do it by rather than this operation. Now we go back to the shape we had here. If you would like to do that with the wire cutting, you should start the cut from the side and then start to do the shaping. In the case of the electronic beam machining, you can start from any position and get the same results. What the hard thing here? What the hardest thing here is to make the vacuum. So they found out that the light actually, which is the laser, which is the light, can do almost the same process, but it's not going to be the same accurate like the electron beam type. So laser beam machining, you're going to use the light energy from the laser to remove the material by the vaporizations, ablations. And the application again to be for the drilling, slitting, slotting, scrapping, and the marking operations. Drilling of the small diameter holes up to 0.025 millimeters, generally used in the thinnest stock because cannot go for deeper than something about 5 or 6 millimeters. The working material is usually going to have a high hardness and strength, soft metals, ceramic, glass, and the glass epoxy, plaster, rubber, cloth, and the wood. Now, what are the disadvantages of the or limitation of the laser? Now, away from the thickness of the parts you like to cut, it does have another disadvantage, which is it's a light. What does that mean? Sorry? No, 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 not that. It's not going to hit your eyes. It's just going to be done there. But you're always almost there. What's happening at the surface is reflection. If we're going to reflect the surface, the light will be dissipated. So you can use it almost on any surface, but it's not going to be a reflected surface. So these are some of the examples you see every day. Well, I don't mean that in real life, but you always see videos for that. Now, the good thing with it is going to have very good surface finishing while you do the operation. It's very good operations can be done by using the CNC machine. Now, if I'm going to have reflective surface, I can simply use the plasma arc cutting, which in this case is not using the electron, is not using the light, is going to use the plasma arc cutting. Plasma stream operating at very high temperature to cut the metal by melting. And the temperature sometimes can reach 13,000 centigrades. The application, most application of the plasma arc cutting involve the cutting of the flat metal sheets and the plates. Now the thickness is going to be much wider than the one we can use with the laser cutting. The hole pressing and the cutting along the defined path can be operated by the handheld torch or automatic by the CNC. Can cut any electrically conductive material. Most frequent metals for the cuts can be the carbon steel, stainless steel, and the aluminum. Now, even the air carbon arc cutting can be used as a type of thermal energy processing, where the arc is going to be generated between the carbon electrode, that the carbon electrode, and the metallic work, and high velocity of the air jet blows away the melted portion of the metal, and can be used to form the curve or to severe pieces, severe piece, or the gouge cavity to prepare the edges for the plates for welding. The problem is that we're going to have the hazard because of the spattering of the molten metals around the place. The work material is going to be the cast iron, the carbon steel, the alloy steel, and the various non-ferrous alloys. Other arc cutting processes using the thermal energy process are the gas metal arc cutting, the shield metal arc cutting, the gas tungsten arc cutting, and the carbon arc cutting. Now that's a very common thing. I think you saw people using this device to cut the metals, especially when they got something very hard to be cut by any other process, like the railroad bars. So it's oxy-fuel cutting operation. That's another thermal energy process because the burning of the fuel will generate very high temperature, and thus we can melt the metals, but the problem is going to be a very bad surface finishing, and also we're going to cause what we call the HAZ, which is the heat affected zone. Burned area, highly affected by the heat, but it's not melted. So we may need an extra operation to do the fixing for this bad surface finishing. So use of heat of the combustion of the fuel gases combined with the thermic reaction of the metals with the oxygen. The popular known as the flame cutting, and cutting torch going to be simply delivers the mixture of the fuel, gas, and oxygen to direct the stream of the oxygen to cutting region. The oxyfuels are the acetylene, which have the highest flame temperature and most widely used, but is very dangerous. We can use the MAP with C3H4, which is known as the propylene, and we can use the propylene, and you can use the propane. The application can be performed manually or by machine. This can be used everywhere, even in the space. How? How we can burn a flame in this space? We can do it even under the water. Because we have our own oxygen, so we're supplying the oxygen and the gas, and we burn them. So we don't need an oxygen because we give it the oxygen directly. It can be, once again, it can be fixed on the machine, or it can be portable. And this is actually the only cutting operation which can be portable. You can take it anywhere, just the gas bottles too, and the hose with the controller valves. Take it anywhere, do the flame cutting. Manual operation example of the application are the repair work, the cutting of the scrap metal, the trimming razors from the sand casting. The machine flame cutting allows for the faster speed and the greater accuracies. And the machine operation often is going to be CNC control to cut the profile shapes if you would like to have a very good cutting. Now, another surprise is it can cut up to 1 meter thickness of the metal. I will show you a photo for that later. Now, in the other process, simply you know that if I'm going to add chemical to some metals, it can simply eat the surface and do the cut. And that's what we call the chemical machining processes. Have you ever tried to put some adhesive material on the foam? Did anyone try that? Well, why everybody here is a good guy except me? I almost tried everything when I was a kid. So actually, if you try to get the UHU tube, okay, the adhesive, try to put it on the foam, leave it for a while, and you will see that it's going to be eroded. The chemicals we have in the adhesive will start to cut the part. So the chemical machining is chemical of a very well-known, non-traditional machining processes, and is controlled by the chemical dissolution of the machined workpiece material by the contact with a strong acidic or alkaline chemical reagents. Special coating called the maskant should be added to protect the area from which the metals is not going to be removed. This process is used to produce the pockets and the contours, as well as the removal of the materials from the parts that have a high strength to weight ratio. Furthermore, the chemical machining method is commonly used to produce the micro components for the several industrial applications, such as the micro-electromechanical systems and the semiconductor industries. Now, just imagine I'm going to use some acids to write down my name on this table. So the steps required to do that, I need to bring a cleaning cloth just to be sure that the surface is too clean. The second step is going to be the masking. For example, I'm going to use the adhesive tape to cover the whole table. Then I'm going to do the etching process. Before the masking, I'm going to bring the cutter, cut on the tape, and remove the parts of my letters. So thus I'm going to have my name is exposed while the whole of the table is going to be covered. Next step is going to be the etching. I'm going to bring the etchant materials, which is a chemical. I can put it by spraying. I can put it simply by the brush, whatever the thing is, immerse it in the acid. So what's happened is that the exposed area is going to be etched down, while the whole surface is going to be protected by the mask. After I finish with the work, I'm going to demask, so I'm going to have my name has been etched on the table. That's the simpler process we have for the chemical machining process. So once again, the masking we can use for the chemical machining are usually going to be added by the cut and peel, like the process I just mentioned. We can use the photographic resistance process, where we're going to have the lights going to do the masking process, where simply I can type the shape I would like to have on the lights, and it's going to do the process of the photoresistance, or I can use the screen resistance type. So that's the photosensitive type, okay, or I can use the peel type. The etching materials, the factor of selection, the etching material is going to be what is reaction with what. So depending on the work material you're going to use, you're going to choose what the etching materials you're going to use for that. Also, some acids or alkaline is going to be have higher reaction with the certain work material. And this will decide what will be the depth and the rate of the material removal. Finally, what will be the surface finishing requirements? Because some of the etching material is going to have very bad surface finishing, while the other is going to give you very fine surface finishing. Now, actually, if you're going to try the adhesive with the foam, is going to give you very bad surface finishing. The etchant also must be matched with the type of the maskant to ensure that the maskant material is not going to be chemically attacked. Okay, so you have to check if it's going to if it's going to affect the masking materials or not. The material removal rate in the CHM is going to be generally indicated by the penetration rate, or how many millimeters we are going to go downward per minute. I don't consider that the material removal rate as a volume, because what I want to know is that the area is going to be constant always, but it's going to be about how the depth of the cutting is going to be occur. The penetration rate is going to be unaffected by the surface area. So it's going to do it by 1 square meter, the same rate as the 2 square millimeters. Typical penetration rate is going to be something between 0.02 and 0.05 millimeter per minute. It's too slow, but it's going to be effective. One of the main problems we have is going to be the undercut. That's my masking material. The chemical is not going to do the things just downward, but also is going to move to the side, because we're going to have exposed surface here. So we're going to have usually the value of U, or the undercut length. What will that cause? That means that the part I will get by the cutting is going to be larger than the one I designed with the maskant. So how to overcome this problem? You mean smaller? Yeah, you make the size, the shape you would like to have, you make it smaller. So the undercut is going to give you the desired shape. Okay, I would like to have it this width, so the masking is going to be cut, let's say 3/4 of this area. So the undercut is going to give me the exact the area I would like to have. So the application we have for the chemical millings are the removal of the material from the aircraft wings and the fuselage panels for the weight reduction. The applicable for the large parts where the substantial amounts of the metals are going to be removed. The cut and the peel methods is the most common method. So once again, we need to clean the part, apply the maskant, scribe, cut, and peel the maskant from the area to be etched. Consider that this area is going to be smaller than the desired one. Add the etchant, so we're going to have the desired cutting dimension because of the undercut, remove, and we're going to have the finished part. One of the applications is going to be the chemical blanking. Now this part is going to be too thin. I cannot use any other cutting operation to do the cutting on it. So instead of that, I can use the chemical erosion to cut these thin shaped. Okay, and again, that. The photochemical machining. So this is a combination of the light and the chemical reaction. We're going to use something called the photoresist masking methods. It's going to apply the chemical blanking and the chemical engraving when the photographic resistance is going to be a method, applies to chemical blanking and chemical engraving when the photographic resistance method is going to be used and used extensively in the electronic industry to produce the interacted circuits designs for the semiconductor wafers. It's also used in the printed circuits broad fabrication process. Possible part geometries in the non-traditional processes are: I can make a very small holes which cannot be done by any conventional methods. I can have the holes with large depth to diameter ratio, holes which are not going to be rounded, a narrow slot and slabs and plates, the micro machining process, the shallow pockets and the surface details in the flat parts, special contour shapes for the mold and the die applications. The work materials for non-traditional machining, actually we can do any parts, any material can be cut with the non-traditional machining. The group of non-traditional machining processes can be applied to metals and non-metals. Certain processes are not suited for certain work metals, so we can simply use another different type of the non-traditional machining. Several processes can be used on metals, but not on the non-metals like the ECM because you use electrical discharge. The EDMY and the EDM type, sorry, this is chemical type, and this is the EDM type, and the plasma arc machining because it cannot be used on the some of the metal materials. So the week we are going to start after the student back, we are going to cover the powder metrology, and I gave you already a hint about the powder metrology earlier. We are not going to simply remove the material. We are going to add the material together and compact them. And that's what we're going to talk about the week after the student back. Now, once again, go back to the trip field before we are going to finish today's lecture. So we have the field trip. Once again, it's going to be to the Blue Scope Steel in Wollongong. And the universities actually provide the transportation. Well, of course, this is a paid trip. If you would like to register for this trip, you have to go to the groups on UTS online, and you will find the group for the field trip to Blue Scope Steel. You can simply add yourself to your to the group and join the people. We still have spaces for 10 students because I know that the bus actually kept, now someone enrolled. So we have now 9 spaces left. If you need to have any information about the registration, you can contact Carlo, the guy in B4, living in the glass room. Okay. So any questions? You finished with the pump? You tested? Who won? You just testing. Okay, yeah. Just tell me who will win. What else? Well, I saw some people did a very big pump. Yeah, I saw some people did that. It was very big one, but with the same stroke length. Anyway, we will see who will winning.